In the last video, I went over head recursion. For this video, I'd like to go over tail recursion. If a recursive call is the last statement in a recursive function, then it is referred to as a tail recursion. If you look at line 16, where I created a tail recursion function, the last statement is a recursive call. After this call, the function does not perform anything. So all of the operations are performed during call time. The function does not perform anything after return time. Let me illustrate this on the right by using a stack frame. When we call main on line 8, a stack frame or an activation record for main is created. And then we go to line 10 and main calls the function tail recursion. And anytime a function is called, an activation record is created. I am going to abbreviate tail recursion to TR. We go to line 16. The argument that we enter in line 10 is 3. We go to line 18. If data is greater than 0, and in this case 3 greater than 0, that is a true statement. If that's the case, then we are going to print data. And in this case, we're going to print 3. So I'm going to just use P to abbreviate print. And here at the bottom, I'm going to write the output. And so we're going to have 3. And then we go down to the last statement, which is on line 23. And tail recursion is called, or there is a recursive call. And in this case, 3 minus 1 is 2. So TR2 is called. And every time a new function is called, an activation record is created. So we go back to line 16, and then we enter the function. And on line 18 is 2 greater than 0. That is a true statement. We print the data. And then we go to the last statement of the function, which is line 23. A recursive function is called. Again, 2 minus 1, this becomes TR1. An activation for TR1 is created. We go to line 16 again. Is 1 greater than 0? Yes, that's a true statement. We print data. We then go to line 23, and 1 minus 1 is 0. So TR1 calls TR0. An activation record is created for TR0. And then we go to line 16 and we enter that function. On line 18 is 0 greater than 0. And the answer is no. And so we exit this if statement. We go on line 25 and 26 and there is nothing left to do. There are no operations. TR0 is popped off the stack. The control is returned back to TR1. Well, since it's a tail recursion, there's nothing left to do. And so TR1 is popped off and the control goes back to TR2. And we go to line 23. There is nothing left after 23. The control returns back to TR3 because TR2 is popped off the stack. And again, on 3R3, there is nothing left to do. And so TR3 is popped off the stack. And our output is 3, 2, and 1. And again, we go back to main. When we reach line 13 for the return 0, our main is popped out the stack. But let me compile this to show you the results. And there it is, 3, 2, 1. Now I'd like to draw a tree graph to demonstrate this tail recursive call. And so once we go to line 10 in main, tail recursion is called. And again, I'm going to abbreviate it for TR. And then we go to line 18, is 3 greater than 0. That is a true statement. And so we go to line 20 and we print that data. 3 is printed. We then go to line 23. A recursive call is made with 3 minus 1 being 2. And so we go back to line 16 for TR2. And we go to line 18. When we enter the function, is 2 greater than 0? The answer is yes. And so we print the data. And in this case, the data is 2. We then go to line 23. A recursive call is made for TR data minus 1. And 2 minus 1, that gives us TR1. We then go back to line 16 and enter the function. And on line 18, 1 greater than 0. And the answer is yes. And so 1 is printed. We then go to line 23. 1 minus 1 is 0. And a function call for TR0 is made. So we go back to line 16 and enter the function. Is 0 greater than 0? The answer is no. So this if statement is skipped and there is no other operations to do. And so this TR0 is terminated. The control goes back to TR1 And again, since it's a tail recursion, TR1 is terminated. The control goes back to TR2. TR2 is terminated since there's no operation afterwards. And then we go back to TR3. And again, TR3 is terminated. We go back to main. Let me use a different color to trace this. You start on the left-hand side. TR3 is called. And so we go down and 3 is printed. And I'll write it here. And then we go to TR2. TR2 is called and 2 is printed. And then we go here and TR1 is called and 1 is printed. And then we go here, TR0 is called and the if statement is skipped. And so we go back up here. We go to TR1 and there's no other operation, so that's popped off the stack. We go to TR2, there's no other operation, so that's popped off the stack. We go to TR3, there's no other operations after that, and so that's popped off the stack and it returns to main. Now how does tail recursion compare to an iterative function? On line 27, I created a countdown function because that is essentially what our tail recursion is doing, it's counting down. Let me illustrate the countdown function. The countdown function, we have I, and I is going to equal data. So in this case, we enter the data 3. And if you look at line 11 in main, I called the function. I went ahead and commented out the tail recursion function so that way we don't confuse the two functions. And as long as I is greater than 0, we're going to decrement, so I minus minus. So what happens is when we go to line 11 and we call the countdown function, an activation record for main is created. Inside of main, we call the countdown, and I'm abbreviating that as CD. And every time we call a function, an activation record is created. Here, CD is created. So we go inside the countdown function, and I is currently set to data, which is 3. And the condition is I is greater than 0. Well, if this is the case, 3 is greater than 0. This will be a true statement. And if that's a true statement, then we go to line 31 and 3 will be printed. And then we go to I minus minus, so I now becomes 2. We look at this condition, I greater than 0. Well, is 2 greater than 0? And the answer is yes. And if that's the case, we print the data. And then we I minus minus. And so I becomes 1. And then we go back to line 29. Is 1 greater than 0? And the answer is yes. And so if that's the case, we go to line 31 and we print out our data, which is 1. I is decremented, so I now becomes 0. We go back to line 29. Is 0 greater than 0? The answer is no. So this becomes a false statement, and we exit out of this for loop, and then we exit out of this function altogether. And so our output is 3, 2, 1. Let me compile this to compare our answers. And there it is, 3, 2, 1. As far as complexities, for time, the countdown function, since we have a for loop, it is going to take a unit of time to count down, so the time complexity will be O of n. And likewise, it's the same for the tail recursion. It's going to be O of n. But in terms of space complexity, if you look at our stack frame, our countdown function only creates one stack frame, and so the space complexity, that is constant. Whereas our tail recursion function, it is going to generate 4 stack frames. And so the time complexity for the tail recursion function will also be O of n. And again, if space and memory is paramount, then I would go with the countdown iterative function over the tail recursion function. The tail recursion is more expensive when it comes to space and memory. So in summary, a function is considered a tail recursion if the recursive call is the last statement of the function. Thank you for watching.